All right, everyone. Welcome to Calculus 1, right? Everyone's in the right place? There's only supposed to be 26 students in here. The only place I see is right here. Here you go. Heck, man. Leave me alone. All right, so you are in math. Make sure everyone's in the right place here. So math 2413, and this is section, I didn't put the section, but we meet from 9 a.m. to 10:40 a.m., right? Those are the times. So my name is Robert D. Giovanni. How many of you have already been into Canvas and been to our website, taken a look at our syllabus? Okay, has anyone not been able to get into the website yet? I just need to see if anyone has not been able to. It's okay. So everyone's good? Okay, so I'm not going to spend time going through the syllabus because you can all read. So I do expect you to go into Canvas, read through the syllabus. That way you know how the grade is broken down. We do have quizzes that are part of your grade. We have in-class exams, of course, a final exam. You need to just take a look at how they're weighted. Quizzes will come in the form of random, just like, hey, here's a quiz, take everything off your desk. Sometimes it'll be a group quiz, sometimes it'll be a take-home quiz. It's very just random. So always be prepared. The homework assignments that I give you are, the expectation is that you would have those completed by the next class. I do not collect any homework. This is calculus, this is grown-up math now. So if I have to check your homework, that means we're in high school again, right? So this is for your own benefit, the homework. If you don't do the homework, you're not going to do well in the class. Now, for those of you who are unfamiliar with my teaching style, I record all my lectures. I will post those on YouTube. There's a link in Canvas right in our main website that says video lectures or something. Click on that and I'll upload this right after class. So it should be up there within an hour of class, unless something happens. The video that you'll see, it'll look real dark, but that's so you can see the contrast of everything on the board. So if it looks like a bad video, it's intentional so that you can see what's written up here. In addition to the videos that I put up, I also have worked out all of the homework problems on video for the entire semester. For those of you who had me for pre-cal, you know that I was not able to keep up with that, and that's because I got thrown into that class at the last minute. This class, I'm very organized. I have all the notes for the whole semester. I have all the video solutions for the whole semester. So this is going to be a much different experience for those of you who had me for pre-cal, which is a good thing because I was hoping to offer that to you in pre-cal, but I couldn't. So does that make sense? That's also on Canvas. So the idea behind the homework solution videos is for you to not just sit there and watch the videos and be like, yeah, sure, I could do that. Yeah, no, I got that. I understand that. Because if you do that, you're going to probably come in and do poorly on the exams. The idea of the homework solution video is for you to try and do the homework. You can have my video up and then try and work out some of the problem and then watch my video and see if we're on the same page. In my experience, that's the best way that video can be utilized for a class like this. Because if you just watch, it's just like when I'm up here lecturing. and I do a problem, everyone's like, yeah, that makes perfect sense. You don't like it already?
I'm in the right class.
Okay. What are y'all waiting for? Where are you supposed to be?
My teacher is
Is it Cal 1?
I think so.
Okay. Go right across the hallway into that room and they can help you. In that glass, right through there, they'll help you. Okay. All right. So, see, that didn't make sense that we had that many people in here. All right, where was I? Homework solution videos. So, utilize those. The idea is that you're not at home like stuck on a problem. You have everything there. Also in the syllabus, it talks about contacting me if you need help. So you have my cell phone number. It's in the syllabus. And I actually got a new phone where I can write on the screen and I can and get back with you. So the way that works, because I teach internet courses, is my students will take a picture of the problem they're working on, then they'll take a picture of their work, nice, neat, clean picture, right? And they'll text it to me, and then what I'll do is I'll look through their work and I'll try and find their errors, and I can kind of circle it and write in my own little things, and then write back anything else that I need to if I need to just create a whole new document. And I can do that sitting on a park bench, in the middle of nowhere. So feel free to use that resource. Don't ever feel like you're bothering me, right? And my job is to be here for you. So, okay. I'm sure I'm missing something, but I think y'all are ready to go. I can tell how eager you are. Yes, questions?
For the notes, are we going to be taking them, or do you have notes that you give out?
Okay, so in Canvas, there's a section called Files, and in there are the course notes. And what I've offered is a printable version of the notes. So you may print those off, and you can bring those to class if you'd like, and you can do your own notes on top of that. Now, I'm not going to grade you on notes, but I'm big on you becoming a good note taker, but at the same time, the whole reason that there's two reasons I record the lectures. One is if you can't be here, then there's something you can go back to. Because when you miss a class, it's like, even when you come back, it's like you feel like you've missed like a month. At least you have that, right? And that's for legitimate excused like absences. I'm not talking about you just went out and partied all night and, you know what I'm saying? So it's there. But then the other part of it is that in class, you can pay a little bit more attention to what I'm doing, what I'm saying, because you can always go back and watch it, right? So you don't have to worry so much about, oh wait, what did he, because it's all going to be there for you, all right? So I want you to be a good note taker, but more just paying attention, understanding what's going on up here. Okay, any other questions? Sure? Okay. All right, well, I think I'm ready to get started. I was ready yesterday, and then the weather, so I had to. I'm sure you were very disappointed if you had Tuesday, Thursday classes, all right? Very disappointed. All right, well, let's get going here. Y'all ready? No more questions? That's it? Yes? There's no binders in this class. No, there's no binder. Now, if you've learned that a binder can help you become organized and stuff like that, I would encourage you to. But in pre-cal, we require a binder specifically so that you can become a better, more organized student. I mean, that's what it's all about. So hopefully you can bring some of those things into this. Yes?
Do we have another contract for the cell phones? So we can't hold it up?
The syllabus does have a policy about cell phones, and it says that you cannot be using your cell phone during class, or else you get kicked out. Yes, but
You get a
10-point penalty on your next exam. So now I would not enforce that today, because I'm going to give everybody a day or two, well, until Monday, right? That's when we come back. On Monday, we're going to take an in-class quiz, and the first question is going to be, I understand the requirements of the syllabus and blah, 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 and you're going to sign off on the syllabus. So that's going to be one of the questions on the quiz. So I encourage you to read that, because if you sign off on that and then Then you pull your cell phone out and I tell you to leave and I count 10 points off the test. And then you're like, what? I didn't know. And you're like, well, you signed, you said you knew. So read the syllabus, all right? Any other questions in terms of that? Okay. All right, let's talk. I have this semester some goals here. All right, so here's my big 2 keywords for this semester. Ready? Here they are. This is my theme for all the classes I'm teaching this semester. Work ethic. So let's talk about that for just a second. We're not going to get all onto these tangential sort of ideas and topics and stuff. I'm going to get to the calculus, and to the math. But let's just talk about work ethic for a moment, if we could. Because I'm not here to lecture you on how to be, personally. But when I put those 2 words up here, what does it make you think? What do those words mean to you? Anyone? Dun, dun. What was that? What do you got?
I feel like how people were raised working, like
Okay.
their parents, like they have a work ethic.
So the parents, you think, have some impact on your work ethic? I agree with that completely. Yes. I saw a hand here. Yes?
It's like, I think it's the quote on your Canvas page that says, practice until you don't get it right, practice until you can't get it wrong.
Yeah, that's right. I think on all my classes I have that quote, and I don't know where I got that quote from. But how's it go? It's like, don't practice till you get it right, practice until you can't get it wrong. Right? It's that really does tie into that idea of work ethic. You don't want to just do some math problems and be like, yeah, I got this. This is fine. You want to do it to the point where you know every problem that you do related to that topic, you just know you're not going to miss it. You understand the concept completely. That's tied into work ethic. Go ahead, Diego.
Being responsible for yourself.
Responsible. Okay, so look, really, when it comes down to it, I've been teaching, you don't even want to know how long I've been teaching. It's been a long time. Early 2000s. At UTSA is where I started, okay? Early 2000s. And the biggest thing that I've seen, the biggest change I've seen in students since then to now is this. And I think the biggest factor, I think, is what's happening in the high schools, in that you're not held to a standard, and you're not, and I can speak personally from experience that I'm having right now, that in high school, they are forced to get students through. That means test retakes, that means whatever. And what the problem with that, the administration will argue, well, if they can retake a test, they've shown mastery of the subject. The problem with that idea, to me, is that it doesn't teach this. That means being prepared on the day of the test, no excuses, you're ready, right? That's work ethic. So I would like for you to think about, what your work ethic is like. Like, are you just half-assing this? Are you really putting in the time and the effort, right? Because ultimately, you have to look at yourself in the mirror and answer that question. And if you're halving it and you're not doing well, then the answer is there, right? So, okay, so let's work on work ethic. And I know some of you already from previous classes, and I know your work ethic already, so that's a good thing. And a lot of you I know nothing about in terms of how hard you work. So if I feel as if students are not doing their homework and they're not putting in the time and effort, then I might just walk around and be like, okay, let me see your homework. Quiz grade, everybody, let's see your homework from last class. And so bring your homework every day. All right, even though it's not required, bring it, because then you have that evidence that you've been working. All right, so let's do it. What's your name, sir?
Ryan?
Ryan? Ryan, can you just open that window real quick?
Yeah.
We just want to make sure real quick. I'm pretty sure, if you don't mind just looking out there, is that a fall all the way down to concrete, or is there a little awning right there?
It's a fall.
Like,
Oh,
you'd die if you went out that window, or you'd survive?
There's an awning.
There's a little awning?
Yeah.
Okay. So, All right, you can shut it because it messes up my the glare on the board. So we always want to think about this, right? Because you never know. It's 2018 and it's a crazy world we live in. So if we hear active shooter, something like that, we need to know what our options are. Everybody should know that that window right there is an exit point, and Ryan will breach the window for us with his chair. No, that's too much responsibility. Everybody over here will breach the window. Everyone over here will hold the door while we get out. No. Right? No, so just, I mean, we need to be prepared, right? So there's an exit point. I believe that this one, let me just look real quick. I believe that this one is not an exit point. So this goes down all the way 3 stories. So that window. Isn't it a wonderful world we live in? All right, let's get down to math. Math's a little more entertaining. Let's do it. All right, so we are going to be using a textbook for this class. The required textbook is Essential Calculus, 2nd edition, Early Transcendentals by James Stewart. If you plan on, well, how many of you need to take Cal 2? Let's do this. How many of you need Cal 2? Okay, so show of hands, you can put your hands down. How many of you, this is it, Cal 1, end of the road? Wow, we got about 50-50 here. Well, I teach Cal 1 like you need Cal 2, all right? Because they go together. So those of you who this is the end of the road, you're going to have to work hard just like everyone else. And for those of you who need Cal 2, my job is to prepare you for Cal 2. So this is the book. If you're going to take Cal 2 and further on, this will cover the entire calculus sequence. So if you buy it once, it'll cover Cal 1, Cal 2, and Cal 3 if you were to take them here. If you go to a different college, then you're going to probably have a different book. All right, so I don't know how much this costs, but if you need it for 2 courses, you can take that cost, divide by 2, and it seems better. And if you take all 3, then divide by 3, and it'll be a bargain, a steal, right? Okay, so please get this book into your possession as soon as possible, just because all of the homework will be assigned from this text. I believe the library does have a copy on hold or on reserve. You can go over there, or just you can talk to one of your classmates, maybe get the problems from them until you get a book. Questions on the text? All right, our schedule. What the heck? I know, but I don't want to be connected. Let me just turn my Wi-Fi off. All right. So the book, the schedule for the topics, the sections we're going to cover, it's again in Canvas. I recommend you print that out and bring it with you, and that way you put it in your binder or whatever, and that way you know what we're doing every day. And we will try and stay on that schedule, as best as possible. I'm not going to actually cover 1.1 and 1.2. So 1.1 and 1.2 in this book, I'm skipping. Now I do have the notes that you can print off and that you can read through, okay? But these are prerequisite ideas, and I like to get right into it day 1. I don't like spending an entire week on review. That's just my thing, because you're so eager to learn right now, right? That a review at this point would bore you to death. No, probably not. But these are the topics that you can go look at. Now, one thing you'll notice in class is that as I work through my notes up here on the board, you'll notice that I have the ability to animate and do things up here, and that's something that you will not be able to do with the notes that you get online, because those are PDFs, those are static documents. But if you are interested in having these documents that you can actually interact with, just meet with me on my office hours or something, and I can give you all these files. But you have to download like a free player, and then you can do everything I'm doing up here. Okay? All right. Speaking of office hours, my office hours are on the syllabus also. And I do have office hours immediately after this class.
You should fix it up, by the way, till 2:45 a.m.
It does? Well, I'm going to be here till 2:45 a.m. No. It does p.m.? It doesn't say p.m.? Okay. I'll take a look at it. Thank you. All right, so I'm going to skip 1, functions and their representations. And then 1, 2 is where we just review all the types of functions that you should know coming into this class. Like, you know, rational functions, trig, all the different trig functions, shifting up, down, left, right, reflections, all that stuff. Now, as we move through this class, it's not going to be like, I expect you're an expert in all of this, and I will help you kind of get the gears going again. But just as a review, you can go back and just see like, okay, these are the things that he was, that this book at least wants us to know. And we're going to get right to the limit, okay, which is 1.3. So that's where we're starting, 1.3. And the limit is the heart of calculus, all right? Just like your body, heart, right? Calculus, all of calculus, Cal 1, Cal 2, Cal 3, differential equations, a lot of mathematics beyond this level relies on this very, very, I'm not going to say simple concept, but it is it's one idea that from it branches out many different areas of mathematics. And so that's what we're going to start with, the limit. And let me tell you about, you know, it's important to know what our goals are, right, in a course like this, like where are we headed. So I don't want to shoot too far. So I'm going to look at real quick just what's our most immediate goal, all right? What's our most immediate goal? Now, I'll get back to the limit, but just I wanted you to understand, like, everything, like, all of the calculus, like, emanates from this simple idea of this limit. Okay, so our first goal, all right, for this class is going to be to understand this expression right here, which is something that we've avoided for a long time. And that's 0 divided by 0. So why is that a problem? You can't divide by 0? You've been told that for hopefully as long as you've been alive, right? You can't divide by 0. So like you can't do 4 divided by 0, right? You've been told that's no-go, right? You've been told pretty much any number, right? Divided by 0, 1 divided by 0, can't do that. Now, what about the other way around? 0 divided by 4, can you do that? Yes, that's okay, and that would be equal to 0. Okay, so that's 0, and then you can flip that one over, and that's okay. So you just can never have the 0 on the bottom, right? This problem right here is almost like worse than division by 0 because it's a combination of two things, I guess you could say. Because if you have 0 on top, right, over any number, the answer is 0, right? So one part of you might be saying, well, look, we have a 0 on top, so 0 over anything should be 0, but then you have 0 on the bottom, which means you can't divide by 0. So this is a huge, like, conundrum, yes? Okay, and this eluded us for a long time, and it was Isaac Newton and Leibniz, another gentleman, who both, independently from one another, they didn't know of each other's existence, at the same period in history, tackled this problem at the same time, and both developed their own versions of calculus. And then later on, you know, they released papers and stuff like that, and so wow, they had the same ideas, right? So there's two fathers of calculus, but they were both going after a problem that was something like this. Now let me show you where you would see something like that, all right? So let's take a visual example to show you when you would get 0 divided by 0. So let's go back to a good old graph here, and let's start out with a line. I'm going to start with a line, then I'm going to put a different graph up here. So let's say that I had a point here and a point here, and I connected them with a straight line. And then I asked for the slope of the line. Okay? So we all know slope is going to be, what slope? Okay, so you're saying y equals mx plus b. That's the equation of the line, right? That's the equation of the line. But the slope specifically is that number right there, isn't it? And how do you get that from this picture if someone actually gives you what these 2 points are? Yeah, so there's a formula for it, right? But if you're just trying to explain it to someone, rise over run, right? You say slope is rise over run. Yes? This all ring a bell? So you could almost look at it as a right triangle. You could go this way also. And you ask yourself, okay, how much do you go up by and over by? That's your rise. That's your run. Right? And so the slope equals rise over run. Technically, the definition is y2 minus y1 over x2 minus x1. Quick side note. If you have a question, this is your opportunity. This is your education, right? You're paying for it or someone's paying for it, right? Don't hesitate to ask questions. At the minimum, make a little notation to come back and ask me if you're too afraid to ask, all right? Because, you know, guaranteed, if you have a question, someone else in the class is going to have the same question. So let's see who's brave. Everyone good so far? Okay. Now, I didn't label this, but what I meant was if this point was x1, y1, and this point was x2, y2, then the definition is the difference of the y coordinates divided by the difference of the x coordinates, right? So we've seen that. Okay, so lines, no problem at all. And then if we go and we look at maybe something like a polynomial function, so let's change it up a little bit here. Let's take some polynomial like that. And let's take 2 points on this graph. Well, this is no longer a line, right? So I can't talk about y equals mx plus b. Like this only works for lines, right? This is some, probably, what degree polynomial could that be? 3. Could also be
Any odd number.
odd, 5. How do you know? How do you know that this is odd degree?
Because they go opposite directions.
That's right. So when you have the left side go down, right side go up like this, you know it's an odd degree polynomial. Now this would also be an odd degree polynomial. This would be even, or this would be even, right? These are things from 1414. So again, let's get the gears going, right? All right, so this is a polynomial, so it doesn't look like this. If I were to connect these 2 points with a line, that's supposed to be straight, then I could find the slope of that line, couldn't I? And I would use the same formula, wouldn't I? But the actual slope of that line doesn't really have anything to do with this polynomial. It's just the difference, it's the rate of change as you go from this point to this point, right? But in terms of the polynomial, it's not a constant rate of change. Do you all agree with that? It's different than this is. But we could still talk about that. And this line has a name. It's called the secant line. Now don't confuse it with the secant function from pre-cal, all right? The secant function is something else. The graph of it looks like something else. But we call that the secant line, all right? Okay. So let's try and add a little bit more to this, because I'm going to get to 0 over 0 here in just a moment. Right now, could you find the slope of that line? Like if I gave you these 2 points, could you do it? Yes, right? Yeah? Okay, so let me add some things here. Let's say that this is time, and let's say that this is distance. And let's call this, let's say in miles, and let's say that your time is measured in hours. Then this polynomial is telling you how far you've gone after a certain amount of time. Would you agree with that? You give me a time, and then this will give you what distance you've traveled, right? Yes, yes? Okay. So what would the meaning be of the slope of this line, this secant line? It would be your rise, right, over your run. Yes? Your rise is a what? Your rise, what is this? This axis is measuring what? Time or distance? Distance, right? So your slope would be the change. I'm going to use delta. Delta. And that's going to represent for us change. Okay? Change. It's your change in distance over what? Run is this way. That's your change in time. Y'all agree? Okay. When you're driving in your car and you look down at your speedometer, it says 35 what? Miles per hour, right? Miles per hour is a fraction. Miles per hour, right? So anytime you have the ratio of distance over time, that really represents distance divided by time is what? Speed or velocity. Although velocity means something different later. In physics, velocity is a little bit different. But here I'll say velocity, okay? So this slope of this line right here would actually represent not the speed of the object, but no, not the speed of the object, but the average speed as it went from this point to this point. It would be the average speed throughout its trip. Does that make sense? Okay, so this right here, I would need more room here. This would be the average speed on interval, I'm going to call it I. So interval I is right here. This interval of time. Okay, so on this interval of time, this rise over run would represent your average speed. Does that make sense? We could throw some quantities in here if it helps us understand it a little bit more. And in fact, I'll do that. Let's say that this was 2 hours, and this was 5 hours, and let's say that this was 30 miles, and let's say that was 100 miles. Then what would the slope of that secant line be? What's your rise? 70, right? So you went up 70 over your run. So what's your change this way? 3. And 70 divided by 3 is approximately what? 2, right? 2 point. Y'all okay? 2.3? 23, sorry, 23, not 2 point. Oh no, this is that bad marker. 23.33333. So that means that your average speed was 23 miles per hour. Does that make sense? You sure? Okay. Now still, at this point, we have not looked at the 0 divided by 0. I've got to get that red off the board right away, or else it won't come on. Okay. Average speeds are great, but Isaac Newton and Leibniz had a more profound question. They wanted to know if it's possible for us to talk about the speed of an object at an instant in time. So like when you're driving down the road and you see, 35 miles per hour on your speedometer, that's supposed to be telling you your speed at that exact moment, right? But that becomes very problematic when you start looking at it from a graphical perspective. Because in order for us to define our speed, we need 2 points, don't we? Right? And then what we do is we connect them with a line and we find the slope, and that would give us the average speed on that interval. If you're talking about your speed at an instant, then what you need to do, well, you tell me, what do I need to do if I'm talking about the speed at an instant?
1 point.
I need to do it at 1 point, right? And that is a major problem, because imagine I try and make this interval of time smaller. So imagine moving this point along this curve. So I'm sliding in this x coordinate, and I'm moving this point over here, and I'm trying to get it to move on top of that one, right? So as long as I have a point that's not on top of this one, I can do secant lines, can't I? But when I move that second point on top of that, what do I get?
0 over 0.
You get 0 over 0. Because, look, if my second point is right on top of my first point, then what's my change in y? There's no change, right? Your rise is 0, and what's your run? 0 also. And that is undefined. But does it make sense to you that there should be an answer? Yeah, there should? Okay, so I'm going to do this with this ruler. I'm going to keep this point right here. I'm going to call this my base point. Keep it there. I'm going to attach the ruler to the other point. And imagine I start moving this point along here. And watch the way the slope of this ruler changes. Okay, so I'm moving it. You see my point coming down? Those are all secant lines, aren't they? And then as I move back up, look at my secant line again. Can you all see that? Okay, and then what happens is I try and get this point on top. And when I get this point right on top, what happens? I get my 0 over 0, right? But look, this slope it's really close to something, right? Like as soon as I get that point on top of the other one, like this thing vanishes and the line goes away because you can't define it, yes? But if I'm just imagine I could like zoom in and zoom in and zoom and zoom and just make the points just barely not on top of each other, right? Then I would have a line. And it looks like it should be somewhere around there, right? And that's what Newton understood, is that we've got to have a way of getting to that slope. We have to have a way around the 0 over 0 because it looks like there's a numerical answer for that. And the way we do it is using what's called the limit. All right? So that's what we're going to start with, the limit. And our goal will be, or at least our most immediate goal will be to be able to find the slope of that line at a single point. And we will define that to be what's called our tangent line. All right? Make sense? Reasonable? Okay. Let's start getting into the limit now. One of the things that is going to have to become very strong for you in a class like this, your algebra skills are going to be tested, all right, in this class. How good you are at algebra is, I've always said Cal 1 is like algebra on steroids, okay? So you're going to be tested big time on whether or not you can factor and do weird algebraic manipulations and all that stuff, clear fractions, conjugates, all that stuff's coming. But more importantly, you have to have a number sense, a sense of how numbers interact with one another. For example, if I just say this to you, let's see if it makes sense. If I take a very, very big number and divide it by a very, very small number, what will I get?
A very big number.
A very big number? Does that make sense to everyone? So, give me an example of a big number. 2 million, okay. How about that 20-year-old that hit the lotto? Y'all hear about that? 20 years old, $258 million. That's a good day, right? Okay, 2 million over, give me a small number. 0.01? Now, we could argue that that's, no, that's not big, and you could say, no, that's not small. But I think for this, we could agree that that's going to be a big number over a small number. So if you take a big number divided by a small number, this should get bigger, shouldn't it? It should be, that should be bigger than 2 million. Yes? Okay, that's what I mean by number sense. You need to understand that that is going to be a big number. Now, what if I flip it over? I take a really, really small number and divide it by a really, really big number. That should be really tiny, right? A lot smaller than this, right? We're going to be playing these games, in your number sense is going to be important here. What if I take a really, really big number and divide it by a really, really big number? Small number? So let me take a really, really big number. I'll have to go with 2 million because someone said that that was big earlier. I'm going to divide that by a really, really big number. I think 500,000 is pretty big. So is that number bigger, smaller? It's that ratio right there. You'd have to divide this by this, right? And you would get some number. But if I flipped them over, you get a different number, right? What I'm trying to get at here is that if I say big number divided by small number, everyone can say that's big. If I say small number divided by big number, everyone can say that's small. But if I say big over big, it depends, doesn't it? It depends on how big these numbers are. And so something like this is harder for us to just spit an answer out like that. Oh, it's going to be big, or it's going to be small. So you'll see this all come into play, but number sense is going to be important. All right, let's bring my notes up. I've got an hour now. Let's see what I can do in an hour. All right, limit of a function. So let's discuss the behavior of this function. This is going to be very visual, so let's see how this goes. Okay, so what I want us to do is discuss the behavior of this function around the value x equals 2. So x equals 2, if you can't see it, is right here. And if I draw this up like that, what does it appear the function's value is at 2? What does it appear like to you? It looks about 8, right? I mean, and you could actually plug 2 into this, couldn't you? And you would get 8. So we know right now, and this is something we would have been able to answer in a college algebra class very easily, is that f of 2 is 8. And that's not what this class is about, all right? But we do need to know that right away, right? The idea of the limit is for us to talk about what's happening not at 2, but near 2. Now, near is a very subjective word. All right, so let me ask you, am I near you right now? Am I in your personal space yet? Are we near? Okay, so am I near SeaWorld?
Relatively.
Relative to what?
So car drive.
Right? Am I near the sun?
Welcome to the universe.
Compared to how close we are, I'm very far away from the sun, right? But I would say I'm near the sun compared to Alpha Centauri, which is the next nearest star. So near is relative, right? Near is a relative word. And we will get around that word by using the limit. But I want you to look at the behavior of this function near to. So when I say near to, what I think I want you to look at it as something like, not 1, that's not near enough, okay? How about 1.5? Nah, not quite. We need to get a little closer. It's like maybe 1.9, right? And then also we could be close to 2 by being on the other side of 2, being like 2.1. Wouldn't that be close to 2? So what is happening near those values? So what I'm going to do now is I'm going to imagine sliding a point from the left side towards the number 2. So look at my x values, 1.4, 1.5. What's happening to my y values, the function's value? It's 6.1, but where is it headed?
It's getting closer to 8.
It's getting closer and closer to the value of 8. At 1.8, I'm at 7.581. So I'm pretty close to 8, right? But you might argue, look, there's a lot of gap between 7.58 and 8, right? So how about I refine this a little bit and start stepping in. How about I go 1.91 now, right? 1.92, 1.93, 1.94, 5, 6, 7, 8, 9. 1.99, look, I'm really close to 8, right? Now this may seem obvious, all right? But this is critically important that you understand that I'm trying to figure out what's happening to this function, not at 2, but near 2. And the first thing I'm looking at is what's happening from the left side. And it appears that as I approach 2 from the left, my values of my function are approaching 8. And I could go even one more step and go to the thousandths position, 1.991, 2, 3, 6, 7. So I'm at right now 1.999. And my y value is 7.996. So I think that's pretty convincing that as we approach 2, the function's value approaches 8. You hear my language there? As we approach 2, the function's value is approaching 8. All right, now that was from the left side. Let's bring that thing back, get it out of our way, and let's just pull it out of here completely. And let's now approach from the right side. So I'm going to come in from the right. Here it comes. So I'm at 3.5. Let's get closer, some 2.5. And look what's happening. It's going up, and then it's passed up 8, hasn't it? But it's going to come back down, and right there, we're at 8.379. So we're bigger than 8, but it's dropping down. And then let's just go to the hundredths here. 2.0, 2.01. 2.00, oops, right there, really close to 2 here from the right, really close to 8, yeah? All right, well, this is a polynomial function, right? Polynomial functions in college algebra, you were told, hopefully, that polynomial functions are continuous. Do you all remember that word? Continuous? What it meant was basically that you could draw this without picking up your pencil. It's a very loose definition. We're going to define it a little more precisely here. But we can pick it up without, or we can draw it without picking up our pencil, which means that if this is 8, if at 2 it's 8, then as I draw it, I should come into 8, shouldn't I? From both the left side and right side, I should come into 8. There should be no like weird craziness happening in there. Yeah? Okay, let's move on to our next example. Okay, so now what we have is a piecewise function. Piecewise functions, again, were done in college algebra, and piecewise functions are 2 different functions that are pasted together to create a new function. So like this one says that, look, if x is less than or equal to 2, we're going to be this function, and if x is greater than 2, we're going to be this function. So they're 2 different polynomials, and we paste them together, and then right here at 2 is where they switch. Y'all seen these before? All right, now there's some subtleties here that I want to exaggerate. Notice that this is a solid dot and this is an open circle, right? That is intentional. That has to be like that. Why can't these both be solid dots? You can't. Yeah, you would fail the vertical line test. You cannot have the function be 2 different y coordinates for the same x coordinate. So good old vertical line test. If we run that test, if these were both solid, it would fail to be a function. So they're not solid. Why is this one solid and this one not? Did I just 50-50 flip a coin and pick, or how do I determine that? It's from this definition up here, right? It says that if x is less than or equal to 2, then you're this, right? And if x is greater than 2, then you're this, right? That's what tells you where the dot goes. So if we're back in a college algebra class, what would f of 2 be? In a college algebra class, if I walked in here and said, what's f of 2? You would plug 2 in where? Where would you plug 2 in?
We would get 8.
You would get 8, but where are you plugging it in? Into the top one, right? Because if you plug in 2 for x, 2 is less than or equal to 2, so you use this one, right? You don't use this one. So if you plug 2 into this, you should get 8. So that's why we get that number there. Right? Okay, now, let's talk about the calculus perspective now. What is the function doing as we approach 2? Where is the function going as I approach 2? It depends. It depends on which way, right? It depends on which side I approach from. This is critical, okay, because we're getting to the idea of this limit, And when you talk about limits, you must talk about both directions. You cannot just choose one side and be happy. It must be from both directions. So let's come in from the left side, and I'll go a little faster through this one. If I come in from the left side, as I approach 2, so here my x values are approaching 2, my y values appear to be approaching what? 8, right? But if I come in from the right side, my y values, they go up. I'm up a little bit above 5. And then as I get closer and closer to 2, right, as I get closer to 2, it appears that it's approaching what? 4. Okay? Now I could refine that a little bit to get us closer. I think you'd be convinced. Are you convinced that it's 4 that I'm approaching? Yes? Okay, so I am approaching 4. Right? So we have 3 different things that we're looking at here. First, what is f of 2? What's f of 2? 8. Okay. What is f? What is f? How do I say this? What is f as we approach 2 from the left? How can I tell you that that's what I'm asking you to do? You understand, like,
Number heading toward the...
yeah, like how do I tell you, like what notation should I use to say that I want you to tell me what this function is doing as I come in to 2 from the left-hand side? Well, you've never seen it before, okay?
0.99, and then 2.01 coming from the right.
Okay, so you're saying I could do like 1.99, right?
From the left
To come from the left?
2.01 come from the
And f of 2.01. Now, this would be me asking you to give me the value of the function at a point close to 2, right? On the left side. And this one close to 2 from the right side. But it's too narrow, because someone might argue with you that that's not close enough to 2. Someone will say, wait, that's the sun, versus us, like what's near, right? So this is possibly not going to satisfy everybody. So we need a notation that lets us know that we're asking the question of what is the function doing as we approach 2 from the left. And here's the notation, okay? Here's the notation. You write limit, okay? This is the idea of the limit. It's not what's happening at a value, it's what's happening near a value, okay? So I'm going to write, sorry, I already messed up. Take the it off there. It's the abbreviation for limit. We don't write the whole word limit. You write lim, okay, which stands for limit, okay? And then you write underneath it x with an arrow towards 2, like that. That tells you, hey, look, the limit right there tells you you're in a calculus class, all right? And that you don't care about what's happening at 2. You want to look at the function, what is as x approaches 2, but I need to tell you from the left side, okay? So from the left side, the way we look at it, when you look at a number line, the left side is where the negatives are, right? And the right side is where the positives are. So what I do is I put a little negative up to the top right of that 2. And that tells you to come in from the left side. Understand? Now, what is it that I want you to what is it that I want you to actually think about? Approaching 2 from the left, right? But of what? Like, what do you want me to approach 2 of? Well, of the function. Okay? So go and approach 2 from the left of this function f. All right? And then tell me what the answer should be. What is it? So what was our answer when we approached 2? When we approached 2 from the left on this function, what did we get?
8.
We got 8, didn't we? We came in and we got 8. And that would be the answer. Understand? Okay. Now, what's the notation to come in from the other side? We write limit, lim, x, arrow to 2, right? Approaching 2. This time, positive, little superscript, we call that, up top right, superscript plus. Be very careful, don't make this mistake. You don't put the negative in front of the 2. Because now you're not approaching 2, you're approaching -2, which is over there, and it's a different part of the graph, right? So these little things have to be in the top right. And I'm looking at the function, right, f of x. And what was the answer? 4. Wait a minute, hold on a second. Hold on a second. I thought if I backed that up a little bit, I thought there was an open hole there, though.
But it's just talking about when you're approaching it.
So it's okay that there's a hole there? This is what the calculus is about. The limit does not care what is happening at the value. The limit does not care that at 2 it's undefined. It doesn't see it, okay? The limit doesn't see it. It only sees what's happening near it. And from what we can tell from this picture, as we approach 2 from the right, the y values, if that's all we could ever look at, were the y values, our y values were doing what? They were approaching 4, weren't they? We have no idea that at 2 it doesn't exist, and it doesn't matter. So the answer is 4. And this is the idea of the limit. I mean, it's a reverse of things that you've done in the past. I'll show you an example, but I'm going to give you a different little example here in a second. But does this make sense to you? This is the first time, unless you've taken calculus, this is the first time that you've ever seen this notation. Do you understand the meanings? College algebra, calculus. Understand? Okay. So let me give you, this was something I saw a guy, he did a while back, many years ago. I thought it was a pretty cool little example. So look, imagine you have, we've all seen a window before, right? Like that's a window, and those are your little pieces of wood or aluminum or whatever in your window. You got your little 4 little window panes here, yes? Okay, so let's say that we have this window here, and let's say that we have little shutters. I'm gonna make little shutters here. Oh wait, there's a better shutter. Okay, so I've got these little shutters here, okay? So here's my window, I've got these shutters. Oh, look in the window, close the window. This is really dumb, but okay. So look. Okay, there's a function. I'm going to stick with 2 because we've been messing with 2. Okay, in college algebra, when you say f of 2, what you're doing is this. You're shutting the shutters and leaving that little gap in the middle, and you're just looking at what's happening at 2, right? That's what you're doing in college algebra by evaluating a function at a point. All right? In calculus, what we do is we open the shutters, all right? And then we imagine, if you can, imagine that that piece of wood, right? That piece of wood is covering up that point now, and you can't even see what's happening here anymore. And you don't care what's happening there anymore, all right? All you care about is what's happening from the left and from the right. Understand? Okay, I don't know if that helps. If it didn't, well, it didn't. All right, let's look at another example. Another piecewise function. Okay, college algebra. Let's get the shutters out. Let's close everything off. What's f of 2? Okay, so if we're back in a college algebra class, f of 2 is 6. At 2, the function is defined right there. At 6, we're done. As we approach 2 from the left, what is the function approaching? So here we go. You know, walking along it, whatever. How high are you? That's what you're asking. And it approaches 8, right? Does it actually ever get to 8? It's not ever going to get there, actually. Like you could plug in a number like 1.999999999 with 1,000 nines. And when you plug that into the